software engineering. And the talk will be given by Sarson Dan from MIT. So it's already on. Yes.
Okay, thank you for the introduction. This is joint work with first of all Jose, who unfortunately couldn't make it today, Nikos, Jasi, Jerry, and Martin. So today we'll be talking about the current state of software engineering. Then we'll talk about what active learning is and how it can be applied to software engineering. Then we'll have a series of case studies and then conclude with challenges and future directions. So what is software engineering like today? Well, it is pretty hard. People spend all day working on difficult and obscure bugs. They have to work with complicated file and network formats. They have to interoperate with other coding systems that aren't necessarily following the spec. And they also have to deal with legacy systems and applications. But it doesn't have to be that way. There's a better life possible. But actually, first let's talk about, here's a job ad from a month ago. If you're an expert in COBOL and JCL and like working on mainframes, there's plenty of great jobs available. But if you don't like that and you prefer to be eating snacks or taking long naps, this is possible if instead you used active engineering to simplify your engineering. So to start off, let's discuss what passive learning is. This is not what we'll be doing in the talk, but we'll explain it so that we can then compare it to active learning. So passive learning is also known as your garden variety program synthesis. You have a fixed set of input and output examples. For example, you have input 0, input 1, output 1, and so forth, and then you run it through some sort of core inference algorithm, and out pops your inferred program. And this is great when it works. However, it has a number of drawbacks. One is because you have a fixed set of inputs, maybe those inputs aren't informative. They might be duplicates, or they might be just very similar and not giving you a very wide variety of outputs. Additionally, in some cases, specifying the input and output pairs can actually be very difficult. Think about binary file formats, for example, and how you'd represent them as data structures. In many of those cases, it might actually be easier just to write the program than to give the input-output examples. And if you had the program, then you could actually have more choice over your inputs. And that leads to active learning. In active learning, we have an existing program implementation. We also have some function that lets us acquire or generate new inputs. We start off with some input, we run it through the program, and that gives us an output. The output is then fed through our core inference algorithm, and it then gives feedback on what the next input we should generate is. And that next input is fed through the existing program. We get a new output, which is fed through the inference algorithm, and so forth. And then we get our next input, output, and then after we've done this sufficiently many times so that we know with high confidence what the inferred program should be, we can then regenerate it and get an inferred program. And these steps at the bottom collectively are program inference. It's repeatedly interacting with a program to derive its model. Now, people often ask us, if we already have an existing program, why would you bother inferring a second program? And the reason is because we can make the regenerated program better than the original. For example, we can omit bugs in the regenerated code. One example of that is because we know what all the array accesses are, we can mechanically add in security checks to prevent buffer overflows. Additionally, we can make the regenerated program faster. We can change algorithms, or we can make it distributed, for example. We can also port the programs to new languages. For example, you could start with a C program and end up with a Python program. Or we could port it to a new environment. Instead of software that runs on your laptop, maybe you get software that runs on your smart refrigerator. People also ask us, well, isn't inferring programs intractable or close to impossible? And certainly, if you had a program like this, where you check, is the input equal to a particular value out of 4 billion, return 1, else return 0, then yes, that's a very difficult problem to infer. And our solutions are twofold. One of them is instrumentation. If we have detailed instruction-level instrumentation that tells us about the branches, then we can infer these types of programs. Alternatively, we can also impose models of computation. We can say that we look at particular types of programs that are well-formed and don't have these obscure cases. This approach of active learning for software engineering can greatly reduce development cost. And the reason is because we can leverage these existing implementations. These are software packages that people have spent millions of person hours working on. These software packages contain mostly correct implementation of core functionality. But what's important is that even though the original code is only mostly correct, for us, that's good enough for inference and regeneration. Because as we mentioned, we impose models of computation that let us iron out the bugs. Additionally, instead of just regenerating existing code, this is also a technique that can be used to simplify development of new code. And we'll discuss that later in the talk. For our case study, we'll be looking at a simplified social network app. Social network apps are extremely complicated. For example, Facebook back in 2011 had 9 million lines of code. And that's 9 million lines of code without even a dislike button. So with 9 million lines of code, it might be considered too difficult to perform inference. Fortunately, however, modern programs have modularity. Facebook, for example, you could consider to contain posts modules, a users module, a groups module, and so forth. And back in 2011, it was estimated to have 10,000 modules. So that means instead of trying to infer 9 million lines of code at one time, it's on average more like 900 lines, which is much more tractable. Our solution space for active learning spans from detailed instruction level instrumentation, which is the most detailed form of instrumentation we can get, to less instrumented forms. For example, you can also instrument at library interfaces, or you can instrument at component interfaces. And the advantage of more instrumentation is you can have potentially more efficient learning. The downside of it is it's going to be more tightly coupled to the original systems. And for our first case study, we'll be looking at detailed instruction level instrumentation. And for our social network, it will be the parsing module. This is important because parsing is a common source of bugs. This is particularly the case when you have shotgun parsers. This is when the parsing functionality is spread all throughout your program. Our case study is called the binary data parser. What it does is it loads Windows bitmap images from a file into an in-memory data structure. For example, if you had this bitmap, we want to store the red, green, and blue pixels. The top left pixel, for example, has a red value of 47, green value of 91, and a blue value of 35. So you might wonder, isn't this really easy? Don't you just directly mem copy from the file into the buffer? However, Windows bitmaps are actually very complicated. For example, they don't actually store it as red, green, and blue. They actually store it as blue, green, or red. If it's 16-bit, it's bit-packed. If it's 32-bit, they also have different configurations of color channels and so forth. Also, the Windows bitmaps are actually stored upside down. That's because it was designed by mathematicians who liked Cartesian coordinates where the lowest row is 0. They also have many different versions, starting from OS2 back in '87 all the way up to Windows 2000. Each of those have different headers and different features. And also, rows are padded to multiples of 4 bytes. What this means is that the bitmap is stored on disk actually differs quite a lot from the pixels stored in your in-memory data structure. What our binary data parser does is you feed it in an image parsing library, such as the open source Parser STV image, and out comes an inferred image parser. So here's the before code from that open source library. And the high level point is it's a lot of code, and also it's complicated because it's trying to parse those variety of image formats in one giant block of code. And what we've managed to infer instead is a simplified parser for a common case. And because we generated this code, we can also easily add in security checks to prevent buffer overflows. And instead of that giant block of code, we have simpler modules that each handle a different type of bitmap image. In ongoing work, for example, this is a decision tree that shows different parsers at the bottom. So those are the leaves in green that each correspond to a particular type of bitmap. And the inner nodes show the header values that we use to decide which parser to call. Binary data parser works by having the original application in the middle, and we perform instrumentation. In our current prototype, it's compiler-based, but in principle, it can also be binary instrumentation-based. It's also given an input space, which is bitmap images, and we run the images through the instrument program to obtain a series of traces. Those traces give us an intermediate representation that tells you the mapping of output bytes as a function of input bytes, and that's fed to our inference engine, which also gives feedback on how to refine the intermediate representation. That inference then gives us new input criteria on what are the new bitmaps we should then try running through the program. And after repeating this process and getting a sound inference, we then perform regeneration and obtain our new inferred parser. Our second case study will look at the database module. And for this, we'll look at component interface level instrumentation. This is the Konya system by Shannon Renard. Their input is a database schema and access to a SQL application. Notice it's just access to a SQL application. There is no source code required. And the output will be the inferred program functionality. So basically, you start with a legacy SQL application. You send it to Konya. Konya then interacts multiple times with this program. And then out comes your shiny new SQL application written in brand new Python code. So here's the data specification that you need to provide. You tell it the name of the database table, which is users. You give the name of some of the columns, such as the name and password fields. And the command specification basically tells you how to run the database program. So this is all pretty simple. And out comes your entire Python application that contains the SQL commands. For example, here has the select statement. It's doing the joins on the database, where clauses, and so forth. At a high level, Konya starts with the application, which has some command line interface. And we also supplied the command and data specification that we mentioned previously. And the queries from the application get sent to the proxy. Notice it gets sent to the proxy, and we didn't actually instrument the original application. Now, any queries from the application get sent via the proxy to the database. The database then sends results, which the proxy sends back to the application. So the application doesn't know that it's been proxied. In the meantime, the proxy has also been recording these traces. The traces are used for inference, and that can be used to also initialize and configure the database. So what this is doing is modular inference. It's not just inferring the program, but it's also inferring the database. And then the inference also sends new commands and inputs back to the original application so that we can do more cycles of inference. And when inference is complete, we then do regeneration and get our new application. So what we've seen so far has been inferring and replacing existing code. With Konya, we have a SQL application, and we get out a better SQL application. With binary data parser, we start with some crummy C application, and we get a better C application. However, we can also use active learning to generate new code. And the reason is because it's easy to write Python programs. Everyone knows how to code in Python. But coding in cloud computing, for example, or airplanes or IoT devices, those are hard. What we can do instead is let people code in Python, and then we do inference to represent that functionality, and then we can automatically regenerate this code that in these new languages that also encode the domain-specific knowledge about cloud computing, IoT devices, and so forth. So now let's look at an example of that. And we'll be looking again at databases, but this will be library interface instrumentation. So this is Nero by Wu, Shen, and Renard. And what we saw with Konya was inferring and replacing existing code. So Konya was an application in any language, but it had SQL. And out of that, you got a Python application with SQL. But what if we didn't have the initial SQL application? Because no one knows SQL, that's a lot more difficult than Python. So what Nero does is you give it a Python application that just uses lists and dictionaries, your regular Python data structures, no knowledge of SQL, and out comes a Python application with SQL. So here's an example of the original Python code. Here we're just reading the first name and last name from an array entry. It's just standard Python data structures. And here is an iterator, standard Python loop, and also you have standard Python conditionals to select the appropriate data. So this is all very simple. And what Nero does is it takes your Python program that has some sort of core application functionality, such as student registration database, and that program just used normal lists and dictionaries in Python. And we observed its behavior with Nero by instrumenting the lists and dictionaries functionality, and then it's converted into a Python application with the same core functionality, but now it talks to a database. And we automatically generate the database, configure it, and make the SQL statements. So here is the considerably more complicated SQL statements that are generated from that Python program. For example, you can see that it's doing an inner join across multiple databases. It has where clauses. You have to select multiple statements and so forth. So what Nero does is you have an application that has a read, evaluate, and print loop, and we perform instrumentation around the lists and dictionary implementation. We give it a seed program, which is the initial Python program that has the functionality you require, and you give it a command and data specification about the function prototypes. We obtain traces from the instrumentation, and that's sent to inference. Inference then gives constraints on new randomized inputs to send back to the application. And then we repeat the inference until it's complete, and then we perform regeneration and get our new database back to application. This has many positive impacts. For example, it greatly reduces development costs because you can remove a lot of bugs, and you can also improve the runtime performance of the program. For example, by changing it from Python lists and dictionaries to a database, you can make it scalable, multi-core, and so forth, and all the benefits of databases. You can also potentially improve the correctness of programs by removing bugs that are security related and also bugs that aren't consistent with your model of computation. However, it can still be correct because you're learning the functionality of the program until you can match all the inputs and outputs. And you can also have security by construction, such as those bound checks. And also, if you're doing heap memory allocation, you can make sure that you don't have any use after free. There are a number of challenges. One is identifying suitable domains. For example, we've mentioned 3 domains, which was BDP, Konya, and Nero, but there's many other domains. But one important problem is providing feedback to users so that users know when their code can't be inferred by the current DSL, domain-specific language. So when designing those domain-specific languages, we want to make sure that they're rich enough to encode the program functionality, but not so rich that inference becomes intractable. And we also want more efficient inference algorithms so that we can work on larger applications. In future work, we plan to look at more ambitious applications, such as the social network as a whole. We want to be able to regenerate more of those smaller modules so that we can then combine them back into the composite. Additionally, we want to learn with noise. At the moment, our program can deal with a limited set of inputs, but it assumes that all the inputs and outputs are going to be exactly consistent with the program. But you can imagine some cases where you might get errors in the outputs. So in this talk, what I've shown is how active learning can simplify software engineering. With binary data parser and Konya, we've shown how we can infer and replace existing code. And with Nero, we've shown that how it can speed up developing new code. And together, these have the potential to revolutionize programming. Thank you.
Yeah, thank you. So this is onward, right? So we're thinking of the future of the world and the software in particular. What you are proposing is, instead of writing detailed programs, perhaps in COBOL, perhaps in some other languages, what you're proposing is to take long naps on the beach, and which is not bad per se, and then use automated infrastructure to infer simple use cases of the complex situations. Do you really believe this is the good way forward? And if yes, then why? Thank you.
Well, it's good because naps are always good. But the point of modularity is that even though we infer small pieces of the puzzle, together they give you the large aggregate systems. So we don't imagine we can infer 9 million lines of code at a time, but maybe 900 is possible. And together that can give you the larger system. Does that answer the question?
You said So you said that doing this in inference, you can actually prevent bugs. But I was wondering if the application you're actually learning from has some functional bugs, won't you learn these functional bugs as well? So won't you inferred program also contain these bugs?
No, because we impose a model of computation. For example, with the bitmap parser, we assume that images are going to be two-dimensional. And if your parser happens to skip some of the pixels in the image, it will actually be detected as a violation.
Okay.
And also, if there's obscure bugs where you feed it some particular input that maybe causes a buffer overflow, those won't be detected if you generate normal, well-formed inputs. So you'll only observe the normal behavior, and you would interpolate out the bugs.
Okay, so you need to add some constraints in the beginning to actually learn the good stuff and not the bad stuff.
Well, there's always some sort of constraint in the learning process, and those well-formedness constraints will let you prevent bugs.
Okay, thanks.
Hi, this is very impressive. A use case that comes to mind right away is the problem I think the OpenOffice team had to deal with reading older binary formats of, for example, the Microsoft Office formats, where you don't have the source code because it's proprietary. And in many cases, it's older versions you can't get anyways. Have you thought about or tried the use case of basically analyzing programs you don't have the source code of in order to be able to read old formats, but you have a running binary, so you can see what the output, or I guess you see the input, but I'm not exactly sure if you would have the ability to get turn that into some kind of structured data that would be useful for loading it into another program or transforming it into a file format that was more readable.
Okay, that's a very interesting idea. Currently, our binary data parser uses compiler-based instrumentation, but in principle, you could do binary instrumentation. And in that case, you could apply potentially binary data parser towards Microsoft Word binary, for example.
Any other questions? Okay, we have plenty of time to discuss.
So I'm curious as to know, if in the process of doing this work, what are sort of the common failure modes of this kind of approach, and do you have some experience of how to get around that?
I would say the greatest difficulty is defining the domain-specific language. For example, the database, it was a create, read, update, delete model, and if you had a program that's more expressive than that, for example, you might not be able, you would have some unusual bugs because some behavior is happening that you're not modeling appropriately, and you wouldn't receive feedback about it.
Any other
So when you learn the program, you also infer variable names, right, in your code? Or didn't I get that? Oh, okay.
Yeah. Well, firstly, with binary data parser, for example, it's compiler-based interpretation. By that time, the variable names have been stripped out. And with the Nero, for example, that was just looking at the databases, not even at the source level. It was interacting with the database, and obviously there are no variable names in that case.
Okay, so you are generating code at some point, right, in this new learning algorithm?
Yes, we do generate code. We try to make the variables somewhat intuitive, like loop counters, I, J, K, and so forth, but you're not going to get the original source level names.
No, and so that's exactly what my question is. So if you say, okay, we infer a new program from the old program, and we generate code, right? You want to change this program because maybe there is some bad behavior and we want to fix it. But is the code that is actually generated, can it be maintained? Can it be understood well enough by people, right? Because you have to think of some generic name, so you lose the meaning of what code is in your inferred program.
Okay. Is your assumption that you have the source code for the original program?
Actually, I don't care if it's black or white.
So if you have generated or synthesized code, then is it readable enough to the programmers to maintain?
Yeah.
Well, in our example of the, I should just search aside. Binary data parser, for example, here's an actual example of the generated code. So some of the variable names could use a bit of work. But there are really two cases. Consider if you had the original program with source code and you have the variable names. If you think that's easier to maintain, you can just modify the original program and then regenerate the code. The alternative is if you didn't have the original source code, then you didn't have the variable names to begin with. So I think in both cases, this is still helpful because you can modify the original program if you have it, and otherwise, you're not losing anything.
Okay, thanks.